All right, welcome to the second video covering fluids. This time we're doing fluid dynamics, aka fluid mechanics. So we'll be looking at fluids in motion. If you took physics in high school, you may be familiar with this first page, continuity and Bernoulli's equation, but we'll go into a little bit more detail talking about viscosity and a couple related things. All right. So, the first thing that we wanted to look at is the continuity equation. And that is this right here. So the idea behind this is that water and pretty much every other liquid is basically incompressible. It takes a huge pressure to get it to change its volume by an appreciable, measurable amount. So for all practical purposes, it's basically incompressible, which means that if you looked at, like if you just held your hand up right here and you tracked how much water per unit time was passing through your hand, however much enters right here is also how much is passing through, leaving right here. The volume per unit time is the same for both of those. So we keep track of that volume per unit time with the flow rate. The volume times the area is the flow rate, Q. So you'll notice from the units, if you have an area times a velocity, so you have that's square meters times meters per second, that's cubic meters per second. That's volume per unit time again. So what this is saying is that if you had, for example, water in a pipe, assuming water doesn't bunch up right there, which it doesn't, because then it would the density would increase, and water doesn't do that because it's incompressible. So because of that, if the regions of the pipe with higher area have a smaller velocity. So for example, if A1, so it looks like A1 has about twice the radius, that would be 4 times the area, right? Because area is proportional to radius squared. So twice the radius or twice the diameter would mean 4 times the area, which means 1/4 of the velocity. So if the area decreases by a factor of 4, the speed of the fluid will increase by a factor of 4. There are closely related things called, if this is the volume flow rate, you can also talk about the mass flow rate, rho times V times A. So this would be kilograms per unit time. So in the case of a compressible fluid, you would track, you would probably have a continuity equation involving this. Rho1 V1 A1 equals Rho2 V2 A2 in a case where the fluid was compressible. But mass still wouldn't, in the steady state, mass wouldn't build up right there indefinitely. Okay, so the next section looks at streamlines in a little bit more generality than before. So this was a streamline in that, if you tracked a little bit of water right here, entering through this area right here, you could track that amount of water as it flowed through the tube. You could do that for any little piece of the water or for the whole pipe. This is called a streamline, and Bernoulli's equation is a statement about these streamlines. So there's also some terminology here with just the fact that we have a streamline means we're talking about laminar flow. So laminar flow means that there exist these steady streamlines. So in other words, if this piece of fluid right here is probably moving this way. If I just look at this position over time, I mean the fluid that's entering there is different. There's fluid that's moving over time. But if I just concentrate on this one point, the fluid, the velocity versus time, if I fix the position, is constant. Right? I could follow that piece of fluid along, and that would be moving. But if I just focus on this particular spot, that flow is steady. We call that laminar flow, as opposed to turbulent flow. So these sections, 14.5, 14.6, are talking about laminar flow. Actually similar with these next few sections as well, 14.7. So everything in the book is on laminar flow. And then we start talking about equations in general. So something out of the book, we give you a little bit of introduction to all types of flow. But yeah, the book is mainly focusing on this nice steady flow, laminar flow. Okay, so back to Bernoulli's equation. This is the version of conservation of energy for fluids. So a fluid can speed up or slow down. So like if it's faster here, then it has more kinetic energy at point 1 than at point 2. There's also potential energy. So we're imagining there's gravity, a gravitational field pointing down. So we have gravity pointing in the negative y direction. This is the y direction. So when I talk about, like in this equation, there's a y1 and a y2. These are with y increasing as you go vertically upwards. And those are like potential energy terms. And then in addition, we also have pressure, this other term pressure, which is another form of like potential energy. So these are actually, so if you look at the units of all of these, it's pascals or dimensions of pressure for every one of these terms. And a pressure is actually the same dimensions as energy per unit volume. So these are also called energy densities. And if you look at, for example, the kinetic energy term, this is like 1/2 mv squared divided by a volume. This is energy density, energy per unit volume. This is potential energy per unit volume. And pressure is a sort of energy density as well. So Bernoulli's equation tracks fluid in a streamline. For any 2 points in the same streamline, you can connect them, or you can relate physical quantities via this equation called Bernoulli's equation. So as one example of this, right here, it looks like there's no change in gravitational height. Like if you go from point 1 to point 2, just the fact that the tube narrows will tell us what's going on with the pressure. So we would take Bernoulli's equation and we would, just to make this clear, we change the color. We would ignore this term and this term. So just focus on the other terms here. And it looks like the speed is moving faster at point 2. So if the fluid in that tube above, if it's moving faster at point 2, that means this term is bigger than this term. So if this term is bigger, then that means P2 must be smaller. So in other words, the pressure here is smaller than the pressure here. And this is a general statement that along a horizontal tube, so you don't have to worry about the gravitational potential energy term, the slower moving liquid is at higher pressure than the quick moving liquid. And we can use this fact actually as a way to measure pressure differences or fluid speeds. So this is called a Venturi tube, which operates under this principle. So because the pipe increases in radius, the flow speed decreases by the continuity equation, and the pressure will increase. So P2 is bigger than P1. And a way to measure exactly how much bigger the pressure is to actually have a small tube connecting the two sides, filling it with a liquid. So here we have like a liquid, and here we have a gas, like air. So the difference between pressure from here and here is not a big deal for air, even though we're going lower in the gravitational field. But for the liquid, a change in height actually has a big pressure change. So this right here, just the fact that the height is a little bit different on the two sides actually will be a big pressure difference. And if this pressure is bigger than the pressure on the left-hand side, then it's going to push harder down on this surface of the water, of the liquid. And that's why this liquid height is lower on the right-hand side. So yeah, the pressure difference will be equal to rho g times the difference in the heights, rho gh. So if you knew something about the pressure differences, you could solve for the height, or vice versa. This is very similar to, so another application you'll have a homework assignment about is a pitot tube, P-I-T-O-T. This is to measure airspeed, but it operates off the same principle here. Okay, now viscosity. So some fluids are more resistant to flow than other ones. For example, maple syrup as opposed to water. Maple syrup has a higher viscosity. So I think you're familiar with the qualitatively what the term viscosity means, but here we actually have a quantitative definition for it. So imagine this is some fixed ground, earth, whatever, whatever you want it to be. And you have control over, you have this plate of some area, and you're dragging it relative to the ground. So your plate is parallel to the ground, and you're moving it relative to the ground. So we're saying the ground is at rest. This is our reference frame, and this thing will be moving with some speed v. So what the water does, and this is a experimental fact, that as long as you're not forcing the fluid to go too quickly, as long as you're in the laminar flow regime, I'm not talking about turbulent flow, what happens is that the velocity of the fluid gradually increases from 0. So like the fluid here would be 0 meters per second anywhere along the ground. Then it would be maybe 1 meter per second for any point right here, 2 meters per second along here, and it gradually increases. The velocity is a function of distance from the ground. It gradually increases to that V max, whatever you're pulling the top plate at. So that's why these arrows are getting bigger and bigger as you go higher and higher. So the fluid speed it kind of transitions from the ground 0 speed to your plate speed that you're enforcing. Okay, so at some speed v, it requires some force for you to do this. And so the bigger the drag from the liquid, the more force you need to get the plate going at some speed. And it depends on how big your plate is, how much water you're dragging along with this. So we define viscosity, eta, this thing that looks like an N, eta, ETA. Eta is defined so that this is true right here. So, and where the length is the distance between the two plates right here. So this is L right here. So the bigger the viscosity, the bigger force required to move this plate at a certain speed. Right? It's definition of viscosity. Then we can use this. So the viscosity is also going to be related to another quantity. And this is what pressure difference is required to get fluid to flow along a pipe. So the setup here, okay, so we're assuming we already know the viscosity now. So we measure the viscosity of some fluid at some temperature is well known. So we know eta at this point. So now suppose we want water or whatever, the fluid, to flow from A to B here. To get that to happen in real life is, because there is some resistance to flow, you actually need a higher pressure here at A versus B, versus on the other side. So how big of a pressure difference do you need? Well, it depends on the viscosity. The higher the viscosity, the higher a pressure difference you need for the same flow rate. Or phrased another way, the flow rate is going to depend on a couple things. It's going to depend on the pressure difference that you set up. So how much water, what's the flow rate? What's the water per unit time that's actually flowing along a cross section right here, or through a cross section right here? It's going to depend on the pressure difference, this delta P. And it's going to depend on the resistance to flow. The resistance to flow is going to be the rest of this equation right here. It's 8 eta L. So eta is the viscosity, L is the length of the pipe, divided by pi r to the 4th. So r is the radius of the pipe right there. So this radius is actually decreasing the resistance of fluid flow, which makes sense, right? The bigger a pipe you have, then the more fluid will flow for a given pressure difference. You know, there's more room for it to flow. And it increases the length right here. So it would decrease the force required for a certain flow. So this equation is called, I can never pronounce this person's name, Puzo. Puzo's law. I don't know. I'm terrible with that. Yeah. So this is flow rate versus viscosity in a pipe. Okay. So everything I talked about before has to do with laminar flow or steady flow. But we could describe fluids in more generality than this, including turbulent flow. So the most general equation here for fluid flow is called the Navier-Stokes equation. So I'm just introducing this, but there's a lot more detail covered in the lecture. This involves a convective derivative. So it's like taking a derivative, but following along with the fluid. So remember before I was talking about a fluid right here, and just looking at this point in space, and even though fluid's flowing in and flowing out, if we just focus on that spot in space, convective derivative will follow along with the fluid. So it's like tracking changes over time, but then following along with it. So you can kind of track this right here, and then this is involving gradients and Laplacians and all sorts of fun stuff. This equation, as intimidating as it looks, so we'll make some simplifying assumptions. I think on your homework for an extra credit problem, we'll make some simplifying assumptions to make this tractable. Another thing you can do is define this thing called vorticity. So the velocity field v, if you define its gradient and its curl, that's almost as good as that's basically defining the function. So first of all, the velocity field will have zero divergence if it's an incompressible fluid. For something like water, any liquid, this is a good approximation. Then we define this thing called the vorticity to be the curl of the vector field. And phrased in terms of the vorticity, this equation takes a much simpler form. So I didn't have time or room to write that equation down, but you can look for that in the lecture notes, see how this equation simplifies when written in terms of vorticity. And then finally, so I was talking about the difference between turbulent and laminar flow. This is a dimensionless parameter called the Reynolds number, which distinguishes which regime you're in. So this number, which roughly, so this is for a pipe, but you can compute this for in general as well. So the density of the fluid, the velocity of the fluid in the pipe, the length of the pipe divided by the area of the pipe. You can get a rough idea for what this Reynolds number is. If this Reynolds number is much less than 2,000, you have laminar flow. So low Reynolds number means laminar steady flow. But really big Reynolds number, bigger than around 3,000. So it's depends on whom you ask for where the transition happens. It's a gradual transition from laminar to turbulent. But above this number, you really start to get turbulent flow. So chaotic. If you track a particular position in space, you can't predict what the fluid velocity is going to look like over time. It's going to kind of randomly change. So this is a good dimensionless number that gives us an idea of what's going on with the fluid. Okay, so I think I gave you more to look forward to here in the lectures, and then summed up the rest of the key equations from the chapter. So yeah, good luck solving the problems.